about sustainable aggregate production, transportation planning. So as you know, production and transportation are two main processes or major processes in a supply chain. So today we are going to address the sustainable development or the sustainability issue within this problem. So let me start with an outline of the speech, which starts with introduction and then problem description and the proposed mathematical model. I will continue with uncertainty handling approach and robust optimization to deal with this uncertainty in the problem. And then I will talk about weighted goal programming and its application to the problem, which is going to address the trial objectiveness of the developed model. And then we will have computational results and model validation with the help of an illustrative example and a set of sensitivity analysis. So as you said, you see here, we will have finally, after the sensitivity analysis, conclusion and future works or our opportunities to extend the current study. And finally, a list of the main references used to provide this study is going to be reviewed. So let me start with the introduction section and talk about production planning. Production planning is known as one of the most attractive issues in manufacturing system. So without any planning, without any production control, we will not proceed with a successful manufacturing system, which seeks to efficiently plan and coordinate all manufacturing activities in order to fulfill and grant all of the goals and, let me say, strategies defined in a company or in the company's organizations, corporates. So we know that production planning is the main element in order to produce the required final products within a supply chain. So supply chain management is dependent on production planning, and we will see that after production planning, the distribution and logistics processes are the second most important ones within a supply chain. Production planning includes the main steps, such as determining the optimal production. I'm talking about the production level of each kind of product in each period of time. The level of inventory on hand, and other essential production parameters deal with demand uncertainty during a specific period of planning. For example, we may consider a daily, let me say, a daily baseline, or let me say weekly manner, or monthly. We may have annually. We may need to provide the production planning for a year, for a given year, for 2 years, for 3 years. So it depends on our strategy. If you're going to talk about long-term strategy, medium-term strategy, or short-term strategy or decision-making, so it depends on how you see your production planning, how you proceed with the demand uncertainty as one of the main, or let me say, major components of production planning. So here you see we are talking about three main elements: production planning, correlated with inventory planning, and then correlated with demand forecasting. So why do we need to forecast demand? Because we cannot say estimate demand with a high probability of precision. You cannot say I'm 100% sure about the amount of demand or demand of customers for this week or for a year or 4 months or 6 months. So demand forecasting, or the ways we are going to treat demand uncertainty, these ways are very important and need to be taken into account within our production planning, along with our inventory planning. Next, we will have transportation planning. Suppose that we are done with our production planning. So what should we do now? We need to come up with some suggestions for our transportation planning, or let me say, come up with decisions regarding transportation planning, because you have now produced or provided your required products based on demand, and now it's time to distribute it through your network, through your supply chain network. So transportation planning is defined as planning required in the operation, provision, and management of your facilities, distribution centers, wholesalers, retailers, and services for the mode of transport. Yani, we may have different kinds of transportation modes. It depends on. We may have trucks, we may have ships, we may have heavy, small trucks, we may have trains, okay? To achieve safer, faster, comfortable, convenient, economical, and environment-friendly movement of people and goods. In this study, we are going to just address economical and environment-friendly movement of goods. But in general, from a more general point of view, it can be applied to the movement of people, as we know as under the category of public transportation. So here we are going to talk about the transportation requirements within a supply chain with the help of our system, our supply chain system. Aggregate production planning. So we were talking about production planning. Next, we will have aggregate production planning. Deals with medium and long-term decision-making processes within our supply chain, and also conducts the management's idea about how much and when materials and other resources must be supplied such that the total cost is minimized. It means that within our aggregate production planning, let me say as the classic APP, let's call it APP. So within our classic APP, the main objective function is to minimize the total cost of your production system, including many components. It may be hiring costs, firing costs of workers, it may be production costs, outsourcing costs, let me say material handling costs, and so on. So within this strategy, within this production system, our aggregate production planning is a subset of production planning itself, which is going to deal with medium and long-term decision-making process, or let me say processes, in which the demand and demand handling is the trigger, or let me say is the starting point of the aggregate production planning. So here we have a figure represents the exact place of APP, considering different activities, processes, or let me say components. Here, for example, it is highly, or let me say it is mainly dependent on demand forecasting, capacity planning, human resource planning, raw materials inventory, finished product inventory, and so on. So in the middle, in the core, we have APP. For example, APP is connected with MPS. MPS is also, it's a very well-known tool within production planning. So you see in the middle, because we are talking about medium range planning or medium term, or sometimes you may have long term, but generally, and let me say, normally APP is dealt with our medium term decision making or planning. So you see, it's in the middle. To review the literature of the APP, because I believe that the combination of APP and transportation planning, this combination has not been yet addressed, or let me say has not been yet addressed enough in the literature. That is why I'm going to start with the APP literature. So APP model was first presented by Holt in 1955. So you see, it's a classic problem. It's an old defined problem. So after that, and since 1955, researchers have been interested and have in this problem and started to work on different components of the problem, or on the application of different models, linear programming models, nonlinear programming models, hybrid models, and let me say different solution algorithms, different solution techniques, exact solutions, heuristic solutions, metaheuristic solutions. And nowadays they are trying to address the role of digitalization within the APP problem. For example, here we have a list of important research works. For example, address multiple objectives instead of just total cost minimization, uncertainty handling, multiple products or multiple sites within a production system or supply chain. They address APP within a supply chain design as part of a supply chain design, or let me say, sustainability and Markov chain-based optimization in order to consider the continuous processes based on time. For example, to define inventory policies within an aggregate production planning problem. For this research, we are going to talk about 3 objective functions, and we are going to develop a multi-objective MILP model. The first objective function is total cost minimization. The second one is total pollution minimization. And finally, the last one or third one is reliability of production system to be maximized. After that, we need to address the uncertainty in our demand parameter. How? We are going to use robust optimization and then apply WGP or weighted goal programming in order to deal with or treat our multi-objectiveness or tri-objectiveness in the first phase of the framework. Finally, we are going to validate the performance or applicability of the proposed methodology using an illustrative example with the help of solver, Cplex solver, since we are talking about linear model, and then with the help of GAM software. Consider a multi-period APP problem. Now we started talking about the problem definition or problem statement. Consider a multi-period APP problem to produce a unique kind of product. So we are not going to talk about multiple products or a variety of products. Suppose that we have just a special product, but we are going to talk about a multi-period APP in 4 seasonal years. So seasonal demand is going to be defined based on interval-based uncertain demands. It is known as the first level of planning because in the second level of planning, we are going to deal with transportation decisions. The problem is then merged with transportation planning in order to directly distribute the products to retailers, wholesalers, our customers, as I said, within the second level of planning. The main assumptions. Now we define the problem. So before developing the mathematical model and formulating the problem, we need to know the main assumptions of the problem. Planning horizon is comprised of 4 seasons within a year. Amount of demand in each period is defined as in an uncertain symmetric interval. All the cost parameters, including production and holding costs, workforce are definitive and certain. Shortage of products is allowed, and this shortage can be satisfied and covered in next periods. Possibility of workforce overtime and outsourcing is taken into account aligned with your normal. So it's not just about, for example, working in 1 shift, 2 shifts. We may consider overtime working, and also in case of any capacity problem, or if the company faces or running out of capacity in order to respond to customer demand, it may take the opportunity of or the option of outsourcing. Amount of inventory and shortage should be 0 at the end of the planning horizon. Manufacturer may fail to provide the required production amount. That is why we are going to talk about this failure within the production system and define the reliability function. And finally, the third objective function would be the expected amount of produced products or manufactured products to be maximized. Environmental pollution occurs due to the production and transportation processes. So we are going to address the environmental pollution within 2 main processes, production and transportation. So within the first or the cover page, we understood that we are going to talk about sustainable APP. So what is sustainable APP and how can we define sustainability within the problem? Since we are talking about total cost, economic aspect, total pollution, environmental aspect, and finally, reliability of system to fulfill the demand as much as possible in order to guarantee the required amount of production, which leads to customer satisfaction. And let me say, social aspect of the problem is going to be addressed along with the previous two previous aspects, we can define it as a sustainable APP. Okay, so this is the name of our problem, and we are going to formulate it. We will start with the first objective function, including 9 terms. So you see, we will have production costs, outsourcing costs, normal working costs, overtime, and finally, transportation costs to be defined in terms of a total cost objective function. And finally, we define it to be minimized. For the second and third objective functions, we will have the amount of pollution for the production or during the transportation activities to be minimized. And finally, the expected amount of produced products within normal work and overtime working to be maximized to ensure that the production system is able to cover or respond to the required demand. We have also a set of constraints: inventory balance constraint, workforce size constraint, because we have the policies, we have defined policies within this problem, or let me say strategy. We are going to hire, and at the same time, we have the possibility to fire or lay off our workforce. We need to define the required man hour to produce a product. Or let me say we need to define the minimum level of workforce or the maximum level within the constraints. And also the capacity of man hour, the maximum allowable man hour. And let me say the maximum capacity of outsourcing. And we have the maximum capacity of hiring and firing. And finally, we have a strategy to have zero inventory and zero shortage at the end of production plan. And also, the amount of demand to be covered is defined as xt, x sub t, as a variable. Why? Because within a given season, we may need to respond to the previous shortage of products occurred, for example, in T-1, T-2. That is why we need to just consider demand plus the amount of shortage to be addressed. And finally, we have the total production or total amount of products, which is restricted to your normal production, in-house production, overtime production, and outsourcing. And let me say, with the help of these constraints and also the domain of our variables, the model development is finished. So we have the model. It's time to talk about uncertainty handling. But before that, we need to show how we came up with reliability function according to the useful life of a system. So we look at the production system, at the production company as a system, as part of a supply chain management system. In reliability engineering, waiting time until failure of the manufacturer follows an exponential distribution. So we are going to consider an exponential distribution for the waiting time until a failure for at the manufacturer site. This failure might be due to the natural disasters, so societal events, terrorist attacks, change in ownership, faults of workers, or weather condition. Therefore, reliability of the manufacturer, or let me say, the reliability of the production system in a given period of time of useful life, for example, 10 years, we may say 5 years, is represented as follows. Based on the reliability engineering concept, we have the definition of reliability, or we are going to use the probability theory and with the help of exponential distribution to calculate the reliability of production system. So the probability of the system, production systems, works without any failure or in a minimum mission time of time. It's equal to e to the power of minus lambda t times time. Okay, you see, it is defined as the reliability of your production system. So average amount of normal and overtime production within your company. We are talking about in-house production, not outsourcing option. is equal to Px times x. We have the product of probability and the production amount as represented in the third objective function. So it's now to talk about uncertainty handling based on the robust optimization techniques. So Bert, Simmons, and Sim claim that it is very rare that all the uncertain parameters of a constraint take different values far from their normal values and at their limit values simultaneously. What does it mean? It means that let's consider an optimistic perspective. We are not going to have, let me say, an ill production system. We are not going to, let me say, put aside our estimations. No, you estimate, you forecast the demand, but you believe that you may have some errors. Okay, you may have deviations from your forecasted errors. So it's not just for all of the system, all of the demand in all the different periods. No, just a part of your forecasted demand may deviate or fluctuate within a, let me say, an interval. So that is why we prefer to apply, or I prefer to apply, Bert, Simmons, and Sim's proposed model in this regard. So for a parameter, we define the following relationship, or let me say, to deal with the nominal value, and let me say, and the deviation value, okay, from the nominal value. So if we say Aij is an uncertain parameter, A bar ij is the nominal value or average value, A hat ij is the deviation. J sub I is the set of uncertain parameters in the ith row of the coefficient matrix of constraints. For example, if you define your constraint for each I, this Ji is defined, okay, for ith row. It means that it shows the size or the number of uncertain parameters. And finally, we will have Aij belongs to the symmetric interval of uncertainty with the help of its nominal value and its deviation value. We have gamma sub I represents the conservative level, and it's known as the budget of uncertainty or budget on uncertainty. It controls the uncertainty, the severity of uncertainty in the problem. Higher values, the higher the gamma, the more severe the uncertainty, we can say. Gamma is determined by a decision by manager within your production system, and its value is dependent on the risk aversion. So if you are a risk averse decision maker, risk averse, so you may consider just low values, or you may consider gamma I equals 1, 0.5, just small values. If you are not risk averse, sorry, I mean, I did it in wrongly. I mean, if you are risk averse, so you are going to prevent from any risk, potential of risk. So you should assign higher values to gamma. But if you are risk neutral, you do not care about risks, okay? You say that I have the required resources at my company in case of any changes or fluctuations in demand, I can easily confront. So you assign a small values to gamma I. So if gamma I is set to 0, the robust model finally turns into a deterministic model. It means that you didn't consider uncertainty in your problem. If you say gamma I is equal to the cardinal Ji, or the number of parameters, cardinality of Ji to be considered, or the number of your parameters, it means that you are considering the worst case. You say all of the parameters may change, or all of the parameters change most probably. Okay, so it is called worst possible values. So we are not going to consider this worst case in the problem, and we will assign a logical value to gamma I. So finally, this is the framework, or let me say the final model proposed by Bert, Simmons, and Sim which was applied to a standard LP problem. And on the right hand side, you will see the modified. And we will have additional or auxiliary variables coming from dual form of the primary model. In this problem, demand parameter is going to be addressed in terms of uncertainty handling. Again, we are going to handle the uncertainty in demand. So we had equation number 23, in which demand plays the key role. So in order to address the Bert, Simons, and Sims formulation within the problem and incorporate it, we have the following modification, or we applied the following accordingly. And rho, we have rho, d hat, and d bar. Rho is the uncertainty level, is a percentage, 10%, 25%, 50%. It depends on your attitude or decision maker's attitude. Note that the other parts of the proposed model will remain unchanged. It means that we are just talking about demand parameter, and we are going to address demand uncertainty. In order to treat or tackle the multi-objectiveness of the problem, we have many solution approaches. We have epsilon constraint, for example. We have lexicographic goal programming. Here is known as one of the most well-known ones, or let me say efficient ones. So that is why we are going to consider the simple extension of this approach. It is known weighted goal programming approach. We are normalizing the deviations of our objective function. That is why we call it weighted goal programming. We define ideal goals for each objective function, and finally the WGP model will try to minimize total deviations from these ideal goals. And finally, we will have a single objective model. Weighted GP provides the importance degree for each objective function, and finally, as I said, normalize the deviations. So you see here, we are defining our IG1 as the ideal value of first objective function, IG2 for the second, and let me say D positive, DI positive, positive deviation from the I objective function. For example, if we have D1 positive, it's a positive deviation from the first objective function. And we have D negative. It is the negative deviation from the objective function. So finally, TCEP, RS are the first, second, and third objective functions respectively. Finally, we will have the following model, including our previous constraints, to be proposed as the final model, final single objective MILP model, mixed integer linear programming model. Now it's time to validate the proposed methodology. That is why we consider a randomly generated example, including 10 customers, 4 transportation modes, and we define most of the parameters with the help of uniform distributions. Here, with the help of CPLEX solver, which is known as one of the famous solvers to solve the linear programming models, within the GAM software, and the execution steps of the GP method is given as follows, are given because we have a set of steps. So these steps are given as follows. First, we need to define the ideal goals. In order to do so, we just optimize the model with the first objective function, and then just with the second objective function, and finally with the third one, in order to extract the ideal values. And then by replacing these ideal values in the final model, we will finally have the values defined for the first, found for the first objective function, second objective function, and third objective function, as well as our deviation values, deviation variables values, and also the objective function of WGP. Now it's time to consider the effects of different conditions of uncertainty, or let me say different levels of uncertainty in the problem. Or let me say, if we just remove or do not care about the uncertainty in the problem, what will happen? For example, if we set gamma equals 0, we will have a lower value for the first objective function, a higher value for the second objective function, and higher value for the third objective function. You see, this is the impact of removing or ignoring the uncertainty in the problem. So these figures represent the effects of uncertainty, considering the uncertainty of demand in the problem, and shows the relationships between both deterministic status and robust status between three objective functions. If we proceed with our analysis, we have a sensitivity analysis section. We are going to consider the effects of changes in the overtime capacity of production and uncertainty level. For example, instead of 25%, we are going to consider 20% increase, 10% increase, 10% decrease, 10% decrease, okay, 20, 10. So we are going to study the behavior of our objective functions against these fluctuations. So what should we do? We just need to consider different change intervals and then incorporate into the model and solve the model for different change intervals and see the effects of overtime capacity first and then uncertainty. So they are not analyzed at the same time, one by one. So we will have the following results. And let me say, with the help of these figures, we can see the behaviors of first objective function, second objective function, and third objective function against our overtime capacity and uncertainty level. So we will have different behaviors. We will have different behaviors for different change intervals. These changes, these fluctuations, these different behaviors, in terms of, let me say, a sensitivity analysis tool, are very useful to predict the required amount of resources, to predict the different possibilities. I'm talking from a managerial point of view. In order to consider, let me say, some options in parallel, or including more subcontractors, or in terms of suppliers, in terms of, let me say, capacity, production capacity augmentation or increase. Why not? Yani if there is such a possibility based on the results, sensitivity analysis results, the management or the manager may consider these opportunities in order to ensure the high efficiency of his or her production system. So it's time to conclude the main contributions or the main findings of the research. A novel, robust, multi-objective mathematical model was developed for designing a sustainable aggregate production planning with the help of uncertain seasonal demand for total cost minimization, total pollution minimization, and reliability maximization. Weighted goal programming to cope with multi-objectiveness. Robust optimization to deal with our demand uncertainty in the problem. And finally, with the help of simplex solver, we try to evaluate the efficiency of the proposed methodology. Objective functions have significant sensitivity to the overtime capacity, which is much more than their sensitivity to uncertainty level within given change intervals. For example, we just considered 20% decrease up to 20% increase. Maybe if we consider 50%, the result is not the same. The first objective increases by increase of uncertainty level and decrease of overtime capacity. The second objective increases by increase of uncertainty level and overtime capacity. The third objective function decreases by increase of uncertainty level and decrease of the overtime capacity. Our two main or key parameters within the sensitivity analysis section: overtime capacity and uncertainty level. For the future studies, we have many options, let me say. We have many options. For example, if you are going to consider a large sized problem, okay, you're going to extend the model, we may need some other solution techniques, approximation algorithms, okay, heuristic, meta-heuristic algorithms. Other uncertainty techniques, fuzzy theory, gray system, stochastic optimal control, Markov chain, okay, Z numbers, all of these techniques, fuzzy theory, gray system, stochastic, Markov chain, can be applied and compared to the results of our robust optimization approach. In terms of human factors, in order to enrich the human factors aspect of the problem, we may include workforce skill levels, along with fatigue or learning options for our workforce. We may consider multiple products within the problem, or we may address the role of digital technologies. Okay, we may extend it to, let me say, a supply chain by including suppliers, by including distribution centers. But let me say, we may also consider a closed loop supply chain. Why not? We have the options in order to extend the current study and include more assumptions. So here we have the list of the main notations, sets, parameters, variables, and finally, the main references used in this study are summarized as follows. And at the end, I would like to say thank you very much for your attention, and also thank you to dear Yiğit Hocam. Yiğit. I'm proud of Yiğit Hocam. And again, thank you very much for giving me this opportunity to have a lecture for your great colleagues, students, and your university. Thank you very much.
Thank you very much, Erfan Hocam. It was a very nice presentation and very interesting also. So you have shed light to different topics covering and resembling from production planning till, you know, transportation, logistic activities, supply chain is included in that. It was really nice, very fruitful. Thank you once again.
Thank you very much. Thank you so much.
And as you have indicated at the end of your presentation, there are different future research opportunities valid and, you know, present in this presentation. So hopefully we can also work on those topics together.
Yes, you're right.
Thank you.
Thank you very much.
Okay, any question to Erfan Hocam from our audience? Would you like to ask anything? From our students, from our professors, any question? No? Okay. So thank you very much, Hocam. Once again.
It was perfect. Thank you very much again for your invitation, kind invitation. It was
Thank you.
my absolute pleasure. Hope to see you again as soon as possible.
Thank you very much.